great. Okay, so welcome everybody. Thanks for being here. There are coffee and cakes in case you haven't seen it. Yeah, I think we're very excited about today's workshop. I will just have an announcement. So now, do you want to have a couple of words about this?
Yes, so we've got funding for around 15 people to go to AI UK, which is a big conference in London, organised by the Alan Turing Institute. And we're also hoping to organise a kind of fringe event to that. So this would be like the afternoon before, where we try and get a lot of researchers, a lot of us, and other institutions to present our work in scientific machine learning. And so yeah, there's funding available for that. So if you're interested, there will be more information put out in the next coming week. But if you are interested, please scan this QR code and sign up. That's not you're not promising to go or anything like that. It's just so we can get an idea of numbers. And we'll also send out the link in the SciML mailing list.
Yes, so it's quite a cool opportunity. So if you're interested in participating. Okay, first is yours.
Thank you. Slides on. So hi everyone, I'm Alasdair. I'm going to talk about SINDy today in a kind of workshop fashion. My supervisors here in Leeds are just the people you see here. I'm also partnered with Fusion Energy, which is based outside Oxford. So I work with these people here. And so just before I get into the talk, I'll just say that this is taken from a couple different places. So it's, you know, my experience with it, reading publications, and then also these two YouTube series are very good. So there's one by Steve Brunton, who's the original author, and then there's another one by his PhD student Alan, which is just a tutorial on using Python version of SINDy. So do check those out if you decide to give SINDy a go. And I'll also mention that Nathan Coots is giving a talk next Monday in Leeds on some SINDy related things. So if you're interested, you should check that out as well. So what is SINDy? So SINDy is just a symbolic regression method, which is, so we're aiming to find dynamical systems of this form. And so really we're trying to find this function f in our system, and we just want a sparse set of equations which describe our data. So an example might be if you've got this measurement data, the line system can you symbolically get this set of equations back out of it. And so that's really what SINDy is used for. So we want to take this kind of time series data and get equations like this back out of it. So to do that, it's quite straightforward. We just take measurements of our state, so column vectors here. So there'll be like x, y, and z for the line system. So we just take measurements in time, construct this matrix, and then we take the for example, the finite difference of it, and construct the derivative matrix. And then our problem just becomes basically a linear regression problem. So we're aiming to find our functions in this matrix theta, which map to the dynamics in x dot. And so theta can really be anything you want it to be. So for example, polynomial basis, like the one shown here. So it's a second order, but really it's just up to you what you want this to be. And so then we need to kind of figure out what am I going to pick for my coefficient. So how do we determine a coefficient? So that's the next thing. And so this is kind of a figure taken from the original paper. And so this is the sort of process that SINDy follows, is we've got some data that's generated on the left. We form our regression problem for each of our equations. So here we've got a fifth order polynomial library. And then we just have to find which of the coefficients reproduce the dynamics. And then our final step really is just to symbolically put that all together. So we just have something that looks like the Lorentz equations. And so that's basically the full process in the original publication. And so as it kind of stands there, there's some advantages and disadvantages. So just starting on the advantages is it's just a simple linear regression. So it's quick, it doesn't need much data. At the end of it, you can generate some interpretable models. So that's kind of what you're aiming for, is a sparse model, which gives you the dynamics, which you can look at and you can kind of physically understand what the terms mean. You can include known physics in it. I'll talk more about how you do that. And then also it's got this PySINDy package that you can use for SINDy. So it's quite easy to generate your own code with it. Some of the disadvantages are your library has to allow sparse representation in your dynamics. So it's hard to know maybe beforehand that that's actually true for your system. Noise can impact the derivative calculations. So for example, if we're using finite differences, we're going to get very noisy derivative estimates. So this is something we need to watch out for. It's not always clear what your relevant features to include are if you're measuring some particular system. So can you do it with limited measurements? I showed you a fifth order polynomial library. So that's an inherently correlated problem. You're constructing a polynomial library. So all these terms kind of look like each other. And so we have to think, how do we optimize a problem where our feature space is likely correlated? And then it also kind of scales poorly with the number of features that we include in our library. So as you increase the number of time series you want to identify over, so for Lorentz we have 3 equations. As you increase that, you're going to really increase the computational problem. And so I'll talk about some methods of getting around some of these things, but there's a lot more that I'm not going to talk about that covers things like this, but just in the interest of time, I won't go over that. And so there's a helpful kind of diagram here of some of the features that are in PySINDy. Again, just taken from the paper. So this was published in 2022. So there's lots of different features. I'll go through some of them. So you've got the optimizers, you've got different kinds of libraries that you can put in, different differentiation methods, and then all kinds of constraining and interesting things over here. Since then, I just added a few things to this figure. There's been, plenty of new additions. There's been new optimizers, new differentiation methods, but these things you see here, like Bayesian SINDy, these aren't actually included in PySINDy. So if you want to use them, you have to go to the GitHub and use them. So as I mentioned before, what we're really the powerful part, I think, of SINDy comes in at this optimization step. So how do we, when we've got this big polynomial library, how do we choose a model which reproduces our dynamics? And so that's really where the optimization step comes in. So we want a simple model, simple as possible, that reproduces the dynamics. So if we just look at a correlation plot of our library, so this is just for the Lorentz equations for second order polynomial library, you can see you've got a lot of correlated features, and not all of them are ones that you want in the equations. And so this is something that we really is like a big challenge in SINDy. So the bigger you make your library, the worse this problem is going to be. And so to get around this, we need some kind of regularization in our problem if we want to generate a sensible solution. And so we can also kind of reduce this problem by putting better data into our system. And I'll talk more about this later. So yeah, something that maybe people are familiar with, but just this should be the L2 norm, sorry, here. But so basically, you can solve this least squares regression problem, and depending on how you pick your regularization, you can get lasso regularization, which is L1, or taken off, which is L2. And so these are kind of traditional methods for solving this type of problem. But for SINDy, they don't particularly work well on their own. So lasso, for instance, is used to generate sparse models, but it's not really the best optimizer to pick, generally speaking, with SINDy. So the one they use in the paper is called sequential threshold at least squares. And there's a lot to look at, but it's quite simple, really. So what it really does is for each equation in our library, we do initial ridge regression guess, and then for a given number of iterations, we essentially threshold the small coefficients in our model. So we get rid of all the terms that are small, and then we regress our problem onto the remaining big coefficients. So this is sequential threshold of least squares. So it's just you iteratively work through cutting out terms until you end up with a sparse model. And so this is one of the commonly used methods, and it actually works quite well, even though it's quite simple. And so finally, I'll just say that if you go particularly deep into SINDy, there is an extra step here at the end, which is called unbiasing, where you basically just perform a non-regularized least squares regression at the end, just to try and fit the data better. And yeah, so just when you use this kind of regularization, it can kind of penalize the model too much. So sometimes you just perform a least regression at the end, least squares regression at the end, just to fit the data a bit better. Sorry, I'll just skip to the end. Okay, sorry about that. So we also might ask, if you've got physical constraints in your model, how could you include those? So again, going back to Lorentz equations, if you explicitly write out the regression problem, you've got to determine all these unknown coefficients. There's 30 of them. But if you knew something about your system, you might be able to cut some of these out. So the Lorentz equations, for example, have this symmetry, which is shown here. And so if you put this into your equations, you essentially see that you use only a certain allowable number of coefficients. So you can really reduce your model space by constraining it. And so this is a good way to get around correlation in your library. So there are lots of different kinds of constraints you can put in to your system. This is just one example, but there's probably like much more interesting ones. But it depends on the data that you're looking at. And so this is something that, like, if you can do it, you should definitely think about doing. So how could we include those within SINDy? So there's optimizers that let you do that. One of them is called constrained SR3. And so essentially it solves this least squares regression, but it's kind of a relaxation of the least squares regression. So it doesn't matter too much about understanding this, but rather than penalizing the coefficients directly, we penalize proxy vector, basically, W. And so this creates a kind of relaxation of the normal regularized problem. And then in here is where we have our constraints. So just below that. So there's a helpful table in the documentation, which just tells you about some of the different functionalities of the different optimizers in SINDy, what they can do and what they can't do. And so I've not gone through all of these here, I've just gone through a couple of them. So for example, with sequential threshold of least squares, you can't have constraints. So that's an important thing to remember. But with with constrained SR3, which is what I mentioned before, you can put those in. So SSR here and frols are greedy optimizers, but I'm not going to talk about those too much. And then there's a benchmarking paper on the different kind of optimizers. So again, if you're interested in what optimizer you need to use, then you can go and have a look at this paper. But if we just look at the figure on the right here, it shows kind of average performance of the optimizers for different models that it's being compared against. And the takeaways basically are that sequential threshold of least squares, this MIOSR, and this weak SINDy here perform quite well. So if you're thinking about using optimizers, these are good candidates to use. So then we move on to the next question, which is like, what kind of data do you need to use in your system? So how much data does it need to put in for a system? When does it work? When does it not work? So if we classify that in terms of kind of the average of Lorentz equations with our Lorentz system, if we classify that in terms of the average number of times around a particular row, we can see that if we look at the top right figure here, that there's essentially a kind of band where we need a certain length of data to get correct identification, and we need it to be sampled fast enough that we get correct identification. So the sort of grayish region here is failed identification, and then above the black line you've got correct identification. And so what's kind of interesting is that sometimes you can still get the correct identification of the system with only sampling one lobe of the Lorentz system, for example. So there's particular cases where you can still get some good models out despite having quite a short sampling of the total length of the data. Basically what I was saying there is that you need to have enough data, you need to see enough of the data to get the correct model. It has to be long enough to really get the correct model out of it. And so for things like multi-scale systems, this creates a lot of problems. So on the top here, you've got some kind of time series, which is varying on quite a quick time scale. And then on the bottom, it's going on a much slower time scale. And so if you want SINDy to work with this, you have to sample the fast and the slow time scales. And so that's using a lot of data. But it's quite easy to work around this in that you can just include burst samplings along this trajectory. So you can just sample your trajectory in bursts and just put that together in your matrix. And that's totally fine to do as a regression problem. And so you can work around that. You can work around these kind of data requirements quite easily. Then there's a question of what kind of data do you need to use with SINDy. So this right figure is a plot of the mean field model up here. So this kind of representation of it's like a simple model flow past the cylinder. And so the data here starts in the near zero at this red dot, and as the amplitude grows in time, it comes down and it starts growing in oscillation, getting bigger and bigger until it reaches this blue called stable limit cycle, where the data basically just continues going around in a circle like that. So depending on where we fit our SINDy model in this particular case, we'll get different answers basically. So while both the top model and the bottom model describe this blue section of data, if you fit SINDy models to the blue section of data, the answer you'll get is a simple harmonic oscillator. It's this thing at the bottom here. And that's because it's the sparser solution of the two. So you do have to be careful about what kind of data you're putting into SINDy. So if you want to get the top model out of this, you'd have to use the full data set. You'd have to include something about the transients. So really for SINDy, the transients are the most important part. And then model selection. Again, what I mentioned before is we want a model that's as simple as possible, but also describes the data. And so one way of doing this is maybe the AIC score. So this includes, it's got a goodness of fit in terms of the log likelihood function. And then it also has a penalty due to the number of non-zero terms in the equation. So basically, if we're adding extra terms, but you're not really adding anything to the dynamics, then the score is going to get bigger. And so that's kind of represented by this dashed curve here in the figure, is that you hope that there's some kind of elbow in our fitting curve where we'll find our optimal models that are as sparse as possible, but also reproducible. So this is one scoring method. There's a lot of different ones that you can think about. And so when we've done all that, we need to think about what kind of basis do we choose. So we need our basis to admit a sparse solution. So this is one of the big assumptions that I mentioned before. And often it's just recommended that you start on a polynomial basis. So start with a low order polynomial basis and just work your way up. Get bigger and bigger, and then if something eventually sort of falls into place with your model and you start getting simple answers, then you're kind of done. But if you think there's other kinds of functions in your data, then you might think about putting those in your library. And then there's also this question of, have I not modeled something with my library? How would I know that? And so if you look at your error in terms of the least squares solution, the error should essentially be the noise in the system. And so this So if you assume your noise is Gaussian, for example, then your errors should be Gaussian, should be distributed in a Gaussian fashion. And then also, as I mentioned, that SINDy doesn't really scale well with a large number of systems that you're trying to identify. So you might think if you've got something like flow path cylinder, which is the top left, so you've got this high dimensional problem in terms of this PDE, you know, how can you get a simple system out of that? And so you might just basically do something like POD on this flow or SVD. And so you break it down into these three modes, these three simple modes. So POD mode 1, there'll be POD mode 2, and then the shift mode. And then you identify a model on this reduced system. And so this is what is actually done in the original paper. And you can see for the full simulation and the identified system, you know, you can capturing something, the correct dynamics there. Another one is if you have implicit dynamics. So in our original formulation, SINDy couldn't identify an equation like this. And so there's a kind of simple workaround for this, and that's to just include implicit terms in your library. And so by including implicit terms in your library, you now need to solve for the null space of data, because now everything is also in the library. So before we were just solving for x dot equals something, but now x dot is in theta, so we need to solve for the null space. But basically what you find is this is quite sensitive to noise. So the better way to do this is to fit an equation to every single term in your library, essentially. So rather than having one equation at the end of x dot equals something, you're going to have an equation for every single term in your feature library. And so obviously this presents a problem now, is how do you pick which equation you want to use to reproduce your dynamics? And so the simplest way of sort of thinking about this is that for equations which are in your model, you tend to get sparse solutions. So just looking at the top of the middle figure there. And for terms which are not in your reproducing equation, you tend to get dense solutions. So you can kind of go through it and sort of see which ones are correct for your model. But this is just an example of one of the sort of extensions of SINDy. There's lots of different ones. There's also extensions to PDEs. So it's just a simple change to your regression model. So before we just had these columns of time. So now you have columns of time and space. And so then you can extend it to try and identify PDEs. You can also subsample the data in the spatial temporal domain, which is shown in the bottom left there. And so that kind of reduces your data requirements. But again, so when you're doing PDEs, you have things like second order derivatives. So this becomes very sensitive to noise. And so there are kind of better ways of doing this. But you'll find if you add something like 1% noise to this, you're not going to get the right equations out of it. So that's the sort of final bit that I'll talk about, is what do you do with noise in SINDy? And so this is one of the big challenges. So here I've got a noisy time series measurement with not even particularly much noise. And then if you take the derivatives of that, that's what you get. So you're trying to fit your data to something like this. And so this is very hard to do now because we've kind of lost all the original information in our data. And so there's a number of different workarounds. And so this is part of what we'll do in the workbook. So one of them is just simply include more data, just put more on and hope that it works. Another one is to use different multiple initial conditions. So like kind of use more diverse data set when you're identifying a model. You could pre-filter the data. That's kind of up to you which filter you'd like to try and use. There's ensembling methods, which I'll talk about. You can constrain your library, which I mentioned before, or you can use this thing called the weak form, which I'll just talk about at the end. So for filtering the data, it's just something like this. You've got some noisy measurements, and then you filter it. So the red line here is the filtered result of the noisy measurements. And then you compute the derivatives on this filtered line. And so you get a cleaner output on that. And so in the original paper, show that kind of this is more robust to noise. A bit better. For ensembling SINDy, it's quite a simple concept really. It's just you've got your time series measurement, and so rather than fitting one model to your time series measurement, you just fit a whole host of models across that data set. So an ensemble of these models, and then you can average the results together. And so this generates more robust models, typically to noise, for the same set of data. And by doing this, you can also get some idea of the uncertainty in your models. So here, for example, you've got a comparison of 1 model, 10 models, 100 models. And so by averaging the results over all these different models, you can kind of create some kind of uncertainty forecast with your identified model. And so there are Bayesian approaches as well, but they're not involved. They're not in PySINdy. So this is one that is in PySINdy. And so finally is just the weak form, and I won't talk about this too much because it's a whole other thing, but this is a very powerful way in SINDy of getting around noise. So if you look at this PDE at the top here, we have a 4th order derivative, and so this is going to be very sensitive to noise. And so to get around that, what we can basically do is multiply it by some weight function W and integrate in space and time over these kind of subdomains in space and time. And then by using the product rule, you can essentially shift the derivative from U onto your function W. So you know what W is, and it's smooth, whereas U is noisy. And so now you can avoid taking the derivatives of U altogether. And so this is a thing called the weak formulation. And this is much better with noise because you can avoid taking the derivatives altogether. So, yeah, so there's a number of different extensions. You can check these out if you feel like it. And there's also a helpful kind of flowchart that's in this publication here, where, if you're trying to fit your own model or your own problem, then you can sort of follow this flowchart and see what kind of methods are best for you. Okay. So that's me. That's all. Thank you. There's references at the end, which you'll be able to see on this slides.
So maybe it's time for questions. Yeah, I can start. So I was wondering, in your research, like if you go through the flow chart, what have you already?
I use a lot of this stuff. I think I've used most things in here at some point. I haven't used the ensembling methods because they actually just came out. That was just added this year. But I do something similar within my data identification. But I think I've used most of these features at some point. Yeah, except maybe control inputs, for example. But at some point, yeah, I've used most of these.
And you have real data. The data you had were not simulated, were experimental data.
I've not used it on experimental data yet. That's what I'm going to do in my placement next month. But I've done it on PDE data and like noisy PDE data and systems where you don't know there's an answer underneath. So a lot of the publications that you see in SINDy, they're kind of the answer is maybe known beforehand, but they're trying to work these things out. So yeah, I mean, but there's a number of papers that use it in cases where you don't know what the correct answer should be, and you can still get sensible out of it. So that's kind of where I've used it. Yeah.
What's somebody mentioned a few slides ago, burst sampling?
So that it's basically just if I go back. So before, just what I was saying is that you've got a time series here which varies on a fast time scale, and this is on a slow time scale. And so to resolve all the dynamics, you have to, you'd have to sample SINDy for like a period of this one, but also a period of this one. So an easy way to do that is finally sample both of these, but just in short bursts. So you're getting the whole length of this time series, and you're getting the kind of fineness of this one as well. So it's just a way of.
So it uses knowledge of like the slower time scale to not knowledge be that.
Yeah, it doesn't use any knowledge of it, but it's basically just you're just capturing both of the time scales in the system. So, but rather than just sampling the whole thing uniformly, which would be like quite, it would use like quite a lot of data. You can just chunk it up into small bits.
Yeah. The first method, we slide on from this, the error percentage goes up a little bit, like you get to 4 or 5 seconds in a couple of slides on graphs. Or maybe 2. Oh, yeah. The small graphs there.
Yeah.
The error increases at 100 models towards 4 seconds. Does the pulse, burst sampling, does that do anything to that? Or can you just do 3 seconds or 4 seconds to improve?
So this isn't used with burst sampling. This is just burst sampling is just one way you can deal with disparate timescales in your identification process. Whereas this is just it's similar, but it's just you're just fitting several different models across your data. You can do it with or without replacements. It's a bagging method, basically. But you probably could implement something similar like burst sampling with the same kind of principle. Yeah.
So in that, the ensemble model is picking the best of all the models.
It doesn't pick the best. Actually, it picks like either the mean or the median, which is not necessarily in the model space. So it is something I think about. But you could equivalently pick the best model if you preferred, but it picks the mean.
If you did pick the best model, would that potentially be prone to overfitting on the range of data that you selected rather than like generalizing to the rest of the time series?
I think it depends how you evaluate the model. Like if you evaluate the model in a completely separate set of data, which is kind of different from the data you train it on, then I would say no.
Do you use different initial states for the ensemble methods?
So it just samples one single time series in this particular case. So you just have one, time series of data, for example, and then you just split that into several different sampling locations and generate models on each of those. And so you can do that with and without replacement. So it can see the same data sometimes or not always. Yeah.
The main one's going to be sort of, as you get more models, and it's not going to happen problems with the outlier models, but a truncated one which discards the most extreme results might help you find something rather than just picking the best one and then still have a range of discard the worst ones.
Yeah. Yeah. I mean that's right. So that might help you deal with outliers, but I guess if you're taking the mean as well as a lot of different models, you might not get your mean might not really be like a sparse model at the end of it, because you could take all these averages and end up with lots of kind of small coefficients everywhere. I think it just kind of depends what you're looking